Okay, so today I want to zip through something real quick. The stuff we're doing today is essentially, it's almost nothing new. The assignment is really just builds on the stuff we've been doing. It doesn't really introduce much, if anything, that's new, except just one concept. So we've been talking about how to transform parent functions, right? To create graphs from very simple starting place, from a simple parent graph. We did that by using translations and a vertical dilation factor. Really, the only thing we're doing new today, and it's not much, is that we're not going to think about H and K as translations. We're just going to think about them as the coordinates of the vertex of any function that starts off with a vertex. Hey, come on now. Let's go. Let's get ready. Any function that has a vertex that starts off at the origin. So two examples would be, and we're going to look at these two, an absolute value function. The parent graph of an absolute value function has a vertex at the origin, and the parent function y equals x squared, where it's just a parabola, has a vertex at the origin. All we're going to do here is we're going to think of the absolute value function in a vertex form that looks like this, and we're just going to plug in the values h and k, which correspond to the coordinates of the vertex, and a, which corresponds to the vertical dilation factor, just like we've been dealing with. You see the subtle difference there, right? Instead of translating horizontally by h and vertically by k, well, we know that if the vertex starts off at the origin with the parent function, if I translate it horizontally by h, then the x coordinate is going to change from 0 to h. And if we translate it vertically by an amount k, then the y coordinate changes from 0 to k. And so we just are going to start with the function without having to move it. We're just automatically going to start by orienting the vertex with coordinates hk. So a is the vertical dilation factor. There is a little trick you can play with absolute value functions. A just happens to be the slope of the right side of the v, but I wouldn't think of it that way because it's not going to work for other functions. It only works for absolute value functions, so you don't want to get in that habit. Instead, just treat a like we have been, as a vertical dilation factor. A is going to be the number we multiply by the parent height to get the dilated height for our graph. Okay. So let's try one of these. How about this guy? Y equals the absolute value of x plus 1 minus 4. So what are the values of h and k? What's h? Negative 1, right? Because h is the number that's being subtracted from x inside the function. So it's negative 1. What's k? Negative 4. Okay, good. And so then we know right away that we need to move our graph over so the vertex is at the point negative 1, negative 4. Okay? The axis of symmetry. Now, the axis of symmetry, there's nothing fancy about that. It's just the vertical line through the vertex, right? If it goes through the vertex, and we know that any vertical line is named by its x values, all the x values are the same for a vertical line, right? The x coordinates. Then what is the equation of the axis of symmetry? X equals what? Negative 1, right? Because we already know an x value. And all the x values are the same. So again, the equation of the axis of symmetry is always x equals h every time for any function with a vertex, okay? We're done with this one, aren't we? Because what's the value of a? What's a in our function here? It's 1, right? So we're not dilating this thing at all. We don't have to change the shape of the parent graph. It just stays the same shape as the parent graph. We just had to move the vertex, and that was it. Okay? Give me 1 to 5. Okay? All right. Let's get a couple more examples in. How about this guy? What are the values of h and k on this one? What's h? 0, yeah. Nothing's being subtracted from x inside the function. What's k? 4. Okay, good. So then we're just going to move this thing up so the vertex has coordinates 0, 4. Okay, so far so good. Now the next step is, what's the value of A? -7. Okay, remember what the job of A is. The job of A is to multiply the parent heights by A to get the dilated heights. And we really only need one of them, because when you're graphing these things in Math Excel, all you need to do is place 2 points using that little graphing tool. You're going to put the vertex where it's supposed to go. Well, that's easy. We know that's just the coordinates HK. And then you need to pick one other point, right? So we just have to pick one convenient one. Well, in our parent function, we know that the shape of the parent graph for absolute value function is just a V, right? So if I go to the right of the vertex by 1, what's the height of the function there? 1, right? I go over 1 and up 1 to get onto the V, right? If I go 2 to the right, the height is 2. If I go 27 to the right, the height is 27 for an absolute value function, right? We're just going to pick the most convenient one to multiply by -7, which is probably just 1, isn't it? Right? If we go over 1 and up 1, well, then we're just going to multiply that parent height of 1. We're going to multiply that by A, which is -7, and we get the result. The dilated height is -7 when I go 1 to the right. Okay, the way you want to think about that is I'm going to go 1 to the right and up 1 times A, 1 times -7. So I'm going up by -7 means down 7, right? And so here we go. We end up with a point right there. We already have a point. The vertex stays in place, right? Never moves. And we can use our axis of symmetry here to reflect this point over the axis to get a free point on the other side. And so if I'm graphing this on graph paper, that's all I need. I'm just now going to connect the dots and make a V, and I'm done. Okay, give me 1 to 5. Okay, no big deal, right? And this is not hard stuff. What about this one? I'll do one more of these absolute value functions. So Nathan, what are the values of H and K here? -1, -2. Very good. So we'll put this guy right there. So the vertex is in the right spot. Okay, what's the value of A here? Hunter. What's the value of A? -6, okay. So then what's that going to tell us to do? If I want to pick a convenient height, like over 1 and up 1, instead of going over 1 and up 1, what am I going to do for my dilated graph? Over 1 and up -6. What's up -6 mean? Down 6. Okay, good. So over 1, down 6. So right there. Now there's my vertex. There's a point. I've got my axis of symmetry, so I can make a reflected point on the other side and just connect them with a V, and I'm done. Okay? All right, so easy stuff. Oh, let's work backward one time. So now the goal here is to start with this graph and write the function that corresponds to that graph. So first of all, what are the values of H and K from the graph? -3, -4 it looks like. Sorry, I wrote that down. -4, +3. Okay, so we're just going to plug -4 in for H, +3 in for K. We got to find A though, right? We got to find A. So our graph, can you tell me right away, has our graph been stretched or compressed? Been stretched? It's been compressed a little bit, hasn't it? How do we know? Let's compare it to the shape of the parent graph, right? What would the parent graph do? Parent graph, if I start at the vertex, and we've done this 1,000 times, if I go 1 to the right, what's the height? 1. Okay, so the parent graph would go through that point. 2 to the right, I go up 2. 3 to the right, I go up 3, etc. So this is the shape of our parent graph, right? So yeah, ours has been compressed a little bit. How much? Well, to find out, we're just going to use the relationship that we have for vertical dilation factor. And some of you already know the answer, right? You can already see the answer. But how would we get the answer if it were trickier? Well, we know that here's the relationship. Parent height times A equals dilated height, right? So a convenient parent height would probably not be 1 this time, because look at the dilated height is a fraction, right? We'd rather have the dilated height be something convenient. So how about if we pick on the blue graph that we're trying to name, we pick the point right there. That's a convenient one, isn't it? Because it's up 1. Okay, so that means I'm going over 2. Normally, I would go up by 2. So my parent height would be 2 times A equals my dilated height. So that's 2. Whoops, get the right color here. So there's a height of 2. Oh my goodness. There we go. There's a height of 2. The dilated height is only 1. So 2 times A equals 1. What's A equal to? 1/2, right? All I got to do is take that little equation and just divide by 2 to isolate A, and I get A equals 1/2. So I just plug those numbers in and I'm done. So A is going to be 1/2. H is -4, so X minus -4 turns into an X plus 4 inside the absolute values. And then K is 3, so I add 3 at the end. There's my answer, right? Okay, good? Good. All right. Shifting to a little bit more complicated functions, quadratic functions. How much more complicated? Almost none. It's almost the same thing. The vertex form for a quadratic function looks almost the same as the vertex form for an absolute value function. Only difference is now the x minus h is where it used to be inside the absolute value function. Now it's inside the quadratic function, right? It's inside the part that's being squared. Okay, but otherwise a is still just the number that's being multiplied out front, and k is just the number that's being added to the whole thing at the end. Okay, so just like before, h and k are the coordinates of the vertex. Just like before, x equals h is the equation for the axis of symmetry. And just like before, a is determining the shape of this thing. Now, one thing I will change, and change this on your notes. A determines the width. Determine the width. What does A determine? Okay, kind of. What's the word we use? Well, okay, but like we talk about the blank of the parent function, the parent blank and the dilated blank. Height. Yeah, we want to talk about a height because that implies there's vertical stuff going on, right? We're not squeezing it and stretching it horizontally. We're squeezing and stretching it vertically. You're changing the height of the function. Okay, we know that if A is positive, we've already established this, the parabola is going to open up. If A is negative, it's getting flipped vertically and opening down. Okay, so then the vertex is showing us a couple things. If the parabola opens up, the vertex is going to be the minimum value of the function. If the vertex opens down, or if the parabola opens down, the vertex represents the maximum value of the function. Okay, that's going to be useful to us here soon. So just for your notes, the vertex form of a quadratic function shows us the vertex with respect to the parent function. The simple parent function is just y equals x squared, or f of x equals x squared. Okay, so let's try this one. Let's graph the function in the red box. F of x equals 3 times the quantity x plus 7 squared minus 5. So first of all, what are the coordinates of the vertex? Yeah, it's the point -7, -5. What's the value of a? 3. Okay, so then the vertex is going to go at that location, and we're going to stretch the function by a factor of 3. Multiply all the parent heights by 3, right? So did we do that? Yeah. Okay, there's my vertex at -7, -5. Okay. What about stretching the function? Well, let's look at this and compare it to the shape of the parent graph, right? The parent graph for a quadratic function, I'd go over 1 and up how far on an x squared graph? 1. I go up 1 squared, which is 1. Okay, Whitney, if I go over 1, I go up 1. What if I go over 2 on a y equals x squared graph from the vertex? How tall is the function there? What's the height? So if I'm graphing a parabola and I go 2 to the right, how far up am I going? Not 2. That's an absolute value function. Remember, a parabola curves up, so the amounts must be getting bigger, right? Over 2, it must be going up more than 4, because it's not a V, it's curving up. I'm going up 2 squared, which is 4. Okay, over 2, up 4, 2, 3, 4. Over 3, up how far? 9. Okay, so I'd go a long ways up then. I'm going clear off the chart up to 9. And that's going to give me the proper shape then, right? The shape is going to be like that. So ours has been stretched up vertically, okay? How much? Factor of 3. So I'm going to take the parent heights and just multiply them by 3. So I get, for example, my parent height of 1 times 3 equals 3. So I'm going to go over 1 and up 3, which I did. What do you know? There it is. Over 2 and up how far? Well, over 2 and up 4 times, I would do 4 times 3 equals 12. So I'd have to go over 2 and I'd have to go clear up 12, which is way off the graph. Okay, you get the idea though? Okay, let's try just quickly here. I think I skipped something on that last page. I did. Okay, what's the equation of the axis of symmetry, first of all? X equals, say it again? -7, right? X equals h, which is -7. Perfect. Okay, so we've got this connection. And what's the minimum value of the function? Karsten, what do you think what's the minimum value of the dark red parabola that we graphed? What's the minimum value? What does minimum mean, by the way? Smallest, yeah. Maximum would be the biggest, right? Oh, very close. You're looking at the right thing. No, you're looking at the right thing. But if we're asking for the minimum value of the function, we're asking for the output value. -5 is the right answer. Yeah. Okay. So the minimum value is -5 because of -5 right there. Okay. Think about that. Like if we're trying to measure, for example, what's the maximum? Say that we're like we did that projectile motion problem, right? Say that we're keeping track of the height of a projectile as a function of time. Okay. if we want to know what's the maximum value of the function for that projectile, which is going to be the height function, right? Height is a function of time. Aren't we looking for the height? We're not looking for the time when it's at its peak, right? If we ask for the maximum of the projectile, we're asking for the projectile motion, we're asking for the maximum output, which is the height. So we're always asking for the y value when we're talking about a minimum or a maximum problem, okay? All right, how about this guy? So graph, this is an easy one, right? There's not much to do here. What are the values of A, H, and K? Okay, so H, and K are -2 and 0 because -2 is what's being subtracted from x inside the function and nothing is being added outside the function, so that's 0. So right away we know that we just want to take this guy and drag it over to there. That's where the vertex needs to go, right? What's the value of A? 1. Do we have to do anything? No, that's it, right? It's just a regular parent graph shape with the vertex at the point -2, 0. And so look, here's our regular shape, right? We go over 1, up 1, over 2, up 4, over 3, up 9. Okay, there's the regular parent graph shape. Let's answer some other questions about this though, because you're going to have a few questions where it's going to ask for more details. Well, the vertex, okay, the vertex is, so that one, we already know that's -2, 0. What's the axis of symmetry? But what we have to write an equation for it. X equals -2. There we go. Good. So there's my axis of symmetry, and it's the line x equals -2. There it is. Okay, the domain. How about that? Domain is the set of x's or y's that are graphed. Which one? X's. Okay, so what if I look at that red graph of that parabola, any parabola for that matter, what's the set of all the x values included in that graph? All reals, because I could zoom out forever, couldn't I? And the parabola is going to spread out to the left and the right forever. And if I were to squish it onto the x-axis, it would cover the whole x-axis. So the domain is all reals, -infinity to infinity. Okay. How about the range? Okay, good. Yeah, the range is the set of y values, right? So there is a minimum y value here. The minimum y value is 0, right? So they're going to go from 0 upwards. The y values increase forever. So 0 to infinity. I need parentheses with the infinity. Ava, what do I have to have with the 0 here? Parenthesis or bracket? Bracket, yep, for sure, because I am including 0, right? Okay. Now, how about this part? This is a little weird. We want to know what is the interval on which the function is increasing. Okay, think about what it means. You've got to think of the definition of increasing. An increasing function is one where if an ant is walking in the positive x direction, so he's moving from left to right across the graph, he's walking uphill. So what are the parts of the domain? So the x values where the function is increasing then. What are the x values where the ant is walking uphill, Julia? What do you think? If an ant's walking from left to right on this red graph, where is he walking uphill? Okay, but where just describe where does he start walking uphill? You're pointing right there, I think, aren't you? Right? Okay, so somewhere there, yeah. So he's going to start at -2, and he increases every place to the right of that, doesn't he? Right? Oh, it takes forever. But it's so the ant is increasing, or the function is increasing on the interval starting at -2 and going to infinity. Here's the question. Do I put a bracket or a parenthesis with the -2? What do you think? So let me ask yourself this question. Is the ant increasing at x equals -2? Is he walking uphill at that point? He's not. That's the transitional point, right? That's where he changes from walking downhill to walking uphill. So the answer is we don't include the vertex in that interval where the function's increasing. Okay? That makes sense? Okay, what about the interval where the function is decreasing? Well, that's when the ant is walking downhill from left to right. So what would that interval be then? Okay, good. Decreasing on the interval from -infinity to -2, bracket or parenthesis? Parenthesis, yep, because there's the point of transition. Okay? All right, we're getting there. Last example. Let's do one more of these. So this time we want to graph this function. So again, same drill as before, right? We just need to know, first of all, where do I put the vertex? What are the values of h and k? What's h? -2. Okay, Owen, what's k? -3. All right. So then we're going to move this guy. So the vertex is at that point. And what's the value of a? 3. Yeah, okay, it's 3. Good. So I'm going to have to stretch this thing by a factor of 3. So we just need, and think about how we do this on Math Excel again with the parabola. You just need 2 points, right? You got to locate the vertex, which we did, and then I have to pick one other point. Well, what if we pick a point that's convenient to multiply by a, which is 3, the height? Anything multiplied by 3 is going to be convenient. 1's probably the easiest, right? So why wouldn't we just use this height? We're going to go over 1 and up 1 with my parent graph. I've got to multiply that by 3, though, to triple the height, right? So we're going to get 1 times 3 equals 3. So that's going to be my new dilated height. I'm going to have to go up 3. And now I've got a point there. I've got a point there. I've got my axis of symmetry that I can use to reflect that point if I'm doing this on graph paper. So I'm going to get a reflected point over on this side. And all I've got to do, if I went over 2, how far up would I go? Normally I'd go up 4, right? But I got to multiply by my dilation factor to find the dilated height when I go over 2. So 4 times 3 is 12. There you go. So over 2 up 12. So that, man, I don't know if I can even go that high. Yeah, I guess I can. That's right there. Right? So I get a point there. I reflect it over and get a point there. And now I just have to connect those. That's not a very good parabola, but you get the idea. Right? Good? Okay. All right. Got a little non-math thing for you. Little non-math thing.